The next step is step 4, and this is to do with determining the smoke layer temperature. We covered in step 1 the design objectives of a smoke control system, and one of the objectives may be to ensure that the smoke does not exceed a certain temperature. This may be for life safety or for property protection. Now we shall look at how to determine how hot the smoke is, and we shall see that this depends upon the rate at which smoke is produced. If we know how much heat is going into the smoke layer by way of the plume, and we also know how much smoke is going into the layer by way of the plume, then we can use a simple formula to derive a figure for the increase in smoke layer temperature above ambient temperature. The formula is shown here. Here we have the temperature rise of the smoke layer represented by theta. Of course, the temperature rise is not going to be uniform throughout the smoke layer, but for our purposes, and at this stage, it is assumed to be the case. In general, it is found that this approximation gives adequately accurate results. Theta is calculated, as you can see, by dividing the convective heat output of the fire by the mass flow rate of smoke and by C, which is the specific heat of air. Let's have a look at how this equation works. Firstly, why do we use the specific heat of air when it's smoke that we're examining? Well, the reason is simply that smoke is virtually 100% air, heated and dirty air, but air nonetheless. Most of the mass flow rate that we calculated earlier is entrained air, and only a very small proportion of the mass flow rate relates to the soot and dust and particles and gases that are actually emitted by the items undergoing combustion. Now that we know that the C we're using is for the correct medium, that is air, why is it in the equation? The easiest way to understand this is to look at the units that are attributed to each of the component variables. We have convective heat output in kilowatts, or as 1 watt equals 1 joule per second in kilojoules per second. And this is on top of the equation, and below this we have the mass flow rate of smoke in kilograms per second and specific heat of air in kilojoules per kilogram per degree C. Specific heat is the amount of energy, measured here in kilojoules, that is required to raise 1 kilogram of material by 1 degree C. Though the value varies slightly depending upon the temperature of the smoke, the value of 1.01 kilojoules per kilogram per degree C is suitably accurate for our purposes here. Let's do an example calculating the average smoke temperature. If we have a convective heat release rate of 5,000 kilowatts and a mass flow rate of 30 kilograms per second, and the specific heat capacity of air is 1.01 kilojoules per kilogram per degree C, we have the equation as shown here. This predicts an average temperature increase of 5,000 divided by 30 times 1.01, which equals 165 Kelvin or 165 degrees C. Let's do another example of the average smoke temperature rise. If we have a convective heat release rate of 6,250 kilowatts and a mass flow rate of 21.4 kilograms per second, we get that theta is equal to 6,250 divided by 21.4 times 1.01, and this equals 289 Kelvin or 289 degrees C. You'll notice that I'm saying Kelvin or degrees C here because a single unit of Kelvin is equal to a single unit of degrees C. They're very similar on the scale, and the units are the same size, but they just start in different places. Let's look at what we've done in these examples. In effect, we've divided the total heat that is contained in the smoke by the amount of smoke to give us a representation of how densely the heat is distributed within the smoke. This representation is converted by the application of the specific heat of air to a temperature rise above ambient, which is theta. The more smoke that is produced, the more thinly the heat within the smoke will be spread out, and so the cooler the smoke will be. For smaller amounts of smoke, the heat is less spread out and is more concentrated, and so we have a hotter mean temperature rise for the smoke layer. Having calculated the average temperature rise in the smoke layer, we can add on the temperature of ambient air to give us the actual average temperature of the smoke layer, and this is the equation we use. In this equation, T0 is the temperature of ambient air, and theta, as we've seen, is the average temperature rise within the smoke layer. TL is the average absolute temperature of the smoke layer. So if we have a temperature rise theta of 86 Kelvin and we take ambient air temperature to be 20 degrees C, which is equal to 293 Kelvin. The average temperature of the smoke layer will be 86 plus 293, which equals 379 Kelvin. As I mentioned earlier, it should be noted that theta can be given in units of Kelvin or degrees C, and this is because it's a temperature rise or a difference in temperature. 1 Kelvin is equal to 1 degree C, so a difference of temperature can be expressed in either unit by giving the same figure. That is, a temperature rise of 15 Kelvin is the same as a temperature rise of 15 degrees C. The average temperature of the smoke layer should be expressed in Kelvin. This is partly because some of the equations that use this result make use of the principles expressed in the general gas law, and this law is concerned with Kelvin and not with the more arbitrary degrees C. Now you should undertake the exercises that involve calculating theta, the average temperature rise in the layer, and TL, the average absolute temperature of the smoke layer. Please satisfy yourself that you are competent in assessing average smoke temperatures.